Hello again, Chemistry 1A. In this recording, I'm going to review the calculations associated with the experiment that perhaps you just watched or certainly should have watched related to the Hess's law experiment, specifically where we calculate the enthalpy of reaction for the sodium hydroxide and hydrochloric acid neutralization reaction. So give me a moment. I'm going to share my screen and show the calculations associated with the data obtained in that trial. Okay, so there we go. You are seeing my screen. This first one is just a PDF of what I showed you in front of the camera earlier. This was my approximation of what your lab book ought to look like. Again, it's not an absolute requirement that it look exactly like this, but certainly should contain the information. Please note that there is a second and third reaction. I'm not going to write them for you. You can and should look them up before you start the experiment. A full listing of the reagents used and their concentration, right? You will list them. A procedure, and as I said in the previous video, do not write the procedure, right? I'll grade you off if you actually write the procedure. That is a complete waste of ink and of your time. Just provide a proper literature reference for the HOL website. And if you don't know how to do that, then I recommend you just Google, a citation engine that helps you create references. This is a pictorial depiction of adding sodium hydroxide and HCl into a new container. And of course, the volume's gone up to contain sodium chloride and water. Initial temperature is as we recorded. Initial temperature of HCl, 19.6, and therefore an average temperature of 19.8. It's important to point out that this is what we're going to call the initial temperature, T sub I, in all of our subsequent calculations. Okay. Curious that it didn't turn this into a PDF, but here's the picture then of the data that I obtained. You saw me writing it all down. 22.3 at the very, very beginning, and then, going up over the first minute or so, and then dropping back down. And as I said during the video, this is exactly what we expect. Even though the temperature of the solution was higher than 32.1, immediately after thoroughly mixing, because this reaction is over as soon as it mixes, basically instantaneously, the thermocouple cannot respond quickly enough to capture the temperature at the moment of thorough mixing and reaction. All right, so we collect all this data, and I'll show you the graph. The pages are out of order, so I'm going to skip past that one and come back to it. Here is the graph. Let me shrink this down a little bit and see if I can rotate it. There we go. Okay, there. I'm not certain if I can squeeze it all in. Please note, I'll shrink it a little bit. There we go. Y versus X, right? Many of you did not provide a proper title on your earlier graphing assignment. Temperature versus time after mixing for sodium hydroxide and HCl. You are going to prepare 3 of these graphs, one for each of the 3 different solutions that you conduct. On the y-axis, temperature in degrees Celsius, 1 division is 0.2 degrees centigrade. On the x-axis, time in seconds, 1 division is 15 seconds. And again, you can see how I've expanded the axes so that my graph takes up most of the page so I can see it. Each of the x's, of course, is one of the points on that previous data table. And please note that I have discounted this data point. That basically means that I have ignored it because the system wasn't at any sense of equilibrium, and this is very clearly off the line. In some statistic courses in upper division chemistry, we talk about how to objectively evaluate data to determine whether or not it belongs in the data set. We're not going to do that here. I just look at this point. I think it's evident that there's something wrong with it. So I have discounted it. The point of collecting the data as time goes on is so that we can back calculate or extrapolate to what the temperature would be at time equals 0, right? This is time equals 0. So this point right here where I have the cursor represents what the temperature would be if, when I mixed them, they mixed immediately, if I put the thermocouple in there immediately, and if it immediately recorded temperature. Of course, none of those things happened. While the thermocouple was coming up to temperature, the system was cooling off. So this extrapolation back to T equals 0 tells me that if I could measure the temperature at the exact moment of mixing, it would have been 32.45 degrees Celsius, right? And let's see if I can, all right, and this is the level of precision that you should be using. Some of you were very sloppy in your previous one, there we go. So if each of these division is 0.2, so there's 32.2, there's 32.4, right there, halfway would be 32.5. This is 32.45. Now, you could get even better and plot all of, enter all of these data points here into a least squares regression program for your calculator, and it would give you the y-intercept. But trust me, it's going to be very, very close to that. And, you know, somebody else might draw a slightly different line here. Nonetheless, 32.45 is the value that we are going to use for T sub F. I'm going to pause here and really try to clarify the use of the term T sub F and time equals 0. So this represents time equals 0. And here's the temperature. Even though it represents time equals 0, we're going to use this as T sub F, T sub final, for our calculations. Okay, so I come up here to the calculations, and I think that these are, I certainly hope that they're not identical. They match in every meaningful way the calculations given you in the HOL website. So one, here's the reaction. Of note, here's the net ionic reaction, and you're going to need to write the net ionic reactions for each of the 3 different chemical reactions. The enthalpy of the reaction, delta H, and this is my abbreviation for reaction, is Q, the heat, that is not the number 9, divided by the moles of reaction, right? Joules per mole. So I need to calculate Q, the heat, and moles of reaction. Let me do those two. Specific heat, 4.18 joules per gram degree C. It's important to note that this is an approximation. This is the specific heat of water, but we had hydrochloric acid and sodium hydroxide solutions. Their specific heats are ever so slightly different, but for the purposes of this experiment, we're going to use the specific heat of water. The mass, we had 20 milliliters in total. We are going to use 1.02 grams per milliliter as the density of the solutions. That's a provided value. And I didn't write on this one, this value is T sub F. This is T sub I, the average of the 2 values. And I go through and I do the arithmetic, 1,079 joules. For the number of moles, 10 mils HCl, a liter is 1,000 milliliters. There's the concentration. I get 1 mole of water per 1 mole of HCl. So I get a value of 0.02. I should have put 2 additional significant figures in here. Alas, I didn't, but I should have done that because I put them down here. And I grant you that is probably 1 more than is appropriate, but for this experiment, I want to carry the significant figures over a little bit more. and I get a value of 53.94, and I see, oops, I should have put a negative on here because that's the amount of heat that's liberated. So I change the sign to 53.94 kilojoules. Now, the known enthalpy for this reaction is minus 55.9 kilojoules. So we're pretty close, minus 55.9, minus 53.94. I offer 5 points of extra credit to the person who explains to me why we might reasonably obtain a value slightly less. So what I'm telling you is that I made no meaningful errors in this experiment. So don't just say it's experimental error. It's not. There is a very plausible reason and very expected reason why this ended up with a value of slightly less than the known value. I'm not going to provide any further guidance. 5 points of extra credit for a either correct or, if not correct, a very plausible explanation. And again, do not invoke errors of one kind or another in the explanation. And that's it. We'll see you in class.